Alright, in this video I'm going to be working Algebra 2 Homework 11.1, which is about composition of functions. So I'm going to be getting out my separate sheet of paper, such as it is, and getting to work. So we're going to find f of g of x and g of f of x. So for a f of g of x, well, f of x is x plus 3, so it's going to be g of x plus 3, which is going to be x over 2 plus 3. And there's not really anything we need to do with that. We could give it a common denominator if we wanted to, but we don't need to. G of f of x is going to be, okay, what does g do? G takes the thing and it divides by 2, so I'm going to replace the x with f of x, and I'm going to divide by 2. And at this point, with these two, parentheses not going to be super important, but I see some of these coming up later that will be. Okay, so when I take f of x and divide it by 2, that's going to be x plus 3, all divided by 2. Alright, for b, f of g of x is going to be g of x minus 5, okay, where g of x is x squared, so that'll be x squared minus 5. That's easy enough. G of f of x, that's where we need to be careful, because what g does is it takes a thing and it squares it. So I'm replacing x with this x minus 5, and that does need parentheses. Now, we could stop there. That would be a perfectly fine equation for g of f of x, but I kind of want to remind you what happens when we square x minus 5. We would need to multiply it out. Never a bad time for me to remind you of that, and if I had to write it in standard form, I'd say that's x squared minus 10x plus 25, right? Because I need to do FOIL. For c, if we're doing f of g of x, f takes a function, or takes a thing, squares it, and adds 3. So this is going to be g of x squared plus 3. And, it might be good to put brackets around that. Okay, or some kind of grouping symbol. So we're taking 3 to the x minus 1, squaring it, and then adding 3. And I think what I'm supposed to be reminding you of here is when we're taking power of a power, that's where we're going to multiply the exponent. So I'm going to take the x minus 1 and multiply it by 2. So I'm going to need to double the x and double the negative 1. So this will be 3 to the 2x minus 2 plus 3. Then if I go to take g of f of x, okay, what's going to happen there? Well, g of x is 3 to the x minus 1. So this will be 3 to the f of x minus 1. Okay, and f of x is x squared plus 3. So this is 3 to the x squared plus 3 minus 1. And so I can do a little something with that. I can say 3 to the x squared plus 2. For d, f of x is 1 over x, and g of x is x squared plus 4. So if I plug in f of g of x, I'm going to be taking 1 over g of x, because f is just 1 over whatever I'm plugging in. Okay, and I've got an expression for g of x. G of x is x squared plus 4. This would be 1 over x squared plus 4. And there's not anything I can do with that algebraically. I guess I could, at the most I could do with this is rewrite this as x squared plus 4 to the negative 1. But there's not any other way I can write that. If I went to take g of f of x, okay, g of x takes something, squares it, and adds 4, so I'm going to take f of x, square it, and then add 4. Okay, f of x is 1 over x, so I'm going to square 1 over x and then add 4. If I squared 1 over x, I'd be squaring the 1 and squaring the x, so 1 over x squared plus 4. But really, both of the bottom two lines are equivalent. I'd say either one of these would be good if you gave it to me on a quiz or a test. But now I'm thinking about it, this type of problem is really well suited to multiple choice, so I need to be able to recognize that they're both the same. That's kind of also part of the point here. E's got a more interesting mix of functions, but if I take f of g of x, okay, f of x is square root x, so I'm going to be taking the square root of g of x, and g of x is natural log x, so f of g of x will be the square root of natural log x. And then g of f of x will be equal to, okay, well, g of something is natural log of that, so it'll be natural log of f of x, and this would be natural log of the square root of x. And the last one, Okay, if I'm taking f of g of x, f takes a thing and it takes the cube root of it. So I'm going to take the cube root of g of x. And g of x is 1 over x plus 6, so I'm taking the cube root of 1 over x minus 6. And yeah, there's not anything I can do with that. I guess at the very most I could say, all right, well, it's the cube root of 1 divided by the cube root of x minus 6, so that would be 1 over the cube root of x minus 6. If you had to write that as a power of x minus 6, we would say it was the negative 1/3 power, but we're kind of getting farther away from our goal here, which is just to write an equation. So g of f of x is going to be, okay, g of a thing is 1 over that thing minus 6, so this will be 1 over f of x minus 6, and f is the cube root of x. This will be 1 over the, whoops, 1 over the cube root of x, subtract 6. Oh yeah, that was a good pair of them to see how that could be differing. So yeah, this one would be like a really good one for multiple choice. Number 2 is going to ask us about some graph table equation situations. I think that'll be good for us. So we've got a table for f, a graph of g, and an equation for h. Okay, so f of h of 2. First, I need to find what h of 2 is. Start with the inside and then work your way out. H of 2, okay, I've got an equation for h. Plug in 2 there, and I'm going to have 2 squared plus 3 is going to be 4, and 3 is 7. Okay, so and I'm taking f of h of 2. I just figured out h of 2 is 7, so this is f of 7. I'm going into the table, that's 6. I'm going to say this is equal to 6. Maybe I should have started this work up here. Yep, that's still visible to you. All right, for b, I'll say, all right, well, I'm going to need to take f of 4 first, so I'll start there. F of 4 is going to equal 0. Okay. And then g of f of 4 is going to equal g of 0, because f of 4 is 0. G of 0 would be the height of the graph right there. That looks like 1. Let's see, I can squeeze one more in here. C is f of 3. Right, well, first we'll find f of 3, and that's equal to negative 1. Okay, and then I'm going to take, okay, f of 3 is the same as taking f of negative 1. I look over here, that's going to equal 4. All right, for D, I've got g of h of negative 1. H of negative 1 is going to equal negative 1. That's a place where we need to be careful with our parentheses. We're going to square that number, and we're going to get positive 1, and then we're going to add 3, and that'll be 4. Okay, so g of h of negative 1 is going to be equal to g of 4. We go over here to the graph. That's 4. I don't know how well that printed on yours. I hope well. That's a height of 6. All right. E. Uh-oh. There we go. I need f of 7. F of 7 is going to equal 6. I've already looked that one up once, yeah. And then h of f of 7, h of f of 7 is taking h of 6. And h of 6, I'm going to take 6 and I'm going to square it. And add 3, and that would be 39. Alright, and then the last one, maybe I'll just zoom out a little bit. It's down here. F is going to be h of 0. Well, h of 0, I'm going to plug in 0 right there for x, and I'm going to get 3. And so h of 0 would be the same as plugging in 3 for h, and that's going to be 3 squared plus 3 more, and that's going to be 12. All right, so that was a good set of graph table equation problems. All right, now we're going to get into the transforms. Okay, so, a lot of these are pretty direct, just like, one transform. But then, kind of in the second column, we're starting to see ones where we have multiple transforms. And in this class, we are really mostly concerned with one at a time transforms. At least I'm going to be in my class. But it would be good for us to practice some of these two at a time transforms. So you can see sometimes there's only one way we can write it, sometimes there's more than one way. I think I've avoided the ones where there's, any ambiguity. But my answers for these are going to kind of all be the same. So I'm going to kind of copy in a skeleton right now. So the graph of G, so each time I'm going to say the graph of G is like the graph of F, because G is just some sort of transform of F, but something's going to be different. I'm just going to write that in for each one. Okay, so for A, replacing x with x plus 1, that's going to shift the graph to left by 1. Okay, so I'm going to say left by 1. Because they shifted left 1 unit, okay, we don't really need to be all that, verbose here. We don't need to be writing a dissertation about these transforms. Okay, that's A. So let's move it on. B is f of x minus 2. If I replace x with x minus 2, I am shifting right by 2 units. So I'll just say, like the graph of f, but right by 2. F of x and then adding 3 after is going to serve to shift my graph up by 3. So I'm just going to say up by 3. And for the same reason, f of x then subtract 4 is going to move my graph down by 4. F of 5x, okay, if I replace x with 5x, that's going to be a horizontal stretch, except because I'm multiplying by 5, it's going to be 1/5 as big. So I'm going to say compressed horizontally by a factor of 5. Or maybe I could say by 1/5. Okay, really doesn't matter to me. 6 times f of x on the outside, that's going to be a vertical stretch. So I'm going to say vertically stretched by a factor of 6. Now for these, I do kind of envision you having your reference sheet nearby that you can just kind of look at. Where we've gotten all the transforms written out, so we can kind of just quickly refer to that. For G, f of x divided by 7, okay, that's 1/7 of x on the inside. That's going to be a horizontal stretch by a factor of 7. Remember, those horizontal transforms, they kind of work the opposite of the way we expect. So if we're dividing by 7 on the inside of the function, it actually serves to make it 7 times as wide. All right, now h is kind of the first of our compound transforms. There's two different things going on here. First, I've replaced x with negative x, and then I've added 1 on the outside. Okay, and I know it was first this and then that because we got to start on the inside of the function. Really think of the, g of x as kind of narratively speaking. What happened to it first? Well, first I take f of negative x, and then I add 1. Okay, so first I need to deal with, what transform does f of negative x represent? Okay, so first it's going to be reflected horizontally, so reflected across the y-axis. And then the plus 1 on the outside, that's a vertical shift that went up by 1. Okay. So, with these compound ones, which isn't going to be something I focus on too much, I'm really going to suggest that you start with the inside of the function and then work your way out. So when we're looking at I and we see 2 times f of x minus 3, we've got that 2 and that negative 3. That's two different things going on. So first I'm going to start on the inside of the function. I'm going to say I'm going to shift right by 3 because I've got x minus 3 on the inside. So right by 3, and then, a vertical stretch by a factor of 2 for that 2 on the outside. So vertical stretch by a factor of 2. Now, for all of these that I'm feeding you right here, the order of these does not actually matter, but I have to say that in general, the order of these transforms will matter. If I was to give you the right combination of them, I think really what I'm doing right here is I'm giving you one horizontal and one vertical, and when I see one that's two horizontals, but I don't think, yeah. Well, I'll think about it. I guess we'll cross that bridge when we come to it. Okay, so negative f of 2x, I'd say, okay, the 2x is going to be a horizontal stretch by half, compression by a factor of 2, compression by half. I don't know what you're going to call that. So I'm going to say horizontal compression by half. I like half because we know it means it's half as big. And then the negative on the outside, okay, that takes a y coordinate and makes it negative. That's going to reflect across the x-axis. Okay, I think we could look at this one of two ways. I don't think it really matters which order it goes in. There's going to be the negative x reflecting across the y-axis, but then there's also going to be the 3, which is going to horizontally compress by a factor of a third. And so, yeah, it really doesn't matter what order you think of them in, as long as we were reporting both a compression horizontally and some sort of horizontal reflection. You could say reflects horizontally, that would be fine with me. I'm going to be most specific and say it reflects across the y-axis, because you can reflect across other lines that aren't the y-axis. I'm not going to do that in this class. For L, g of x equals 1 minus f of x. I'm going to go off to the side. I'm going to rewrite this a little bit. I'm going to call this negative f of x plus 1. I think that'll be a little easier for us to look at and see what's going on. Okay, first I've got the fact that f of x got multiplied by negative 1. Okay, so that's going to be reflection vertically. Okay, vertical reflection, reflect across the x-axis. And then I'm going to shift up by 1. And this is one where the order would matter. So what I'm going to do is I'm going to say, all right, let's just start with this point in red, and then we're going to kind of do these two things in different orders. First, we reflect across the x-axis, and then shift up by 1, and say maybe it was, not all the way back. Okay, so I'd end up, closer to the x-axis, but negative. But if I shifted up by 1 and then reflected, I'd end up farther away. Okay, that would be my resulting point. So the order here does matter. Okay, and so but also the order I wrote it in is true, right? First I multiplied by negative 1, then I added 1. But you could also have written this as, I'm not sure why a person would do this, but the negative of f of x minus 1. Yeah, a negative f of x and a plus 1. So you could say that this is like moving down 1 first and then reflecting across the x-axis. But I wouldn't recommend doing that. I just wanted to point out that sometimes these are confusing and there's more than one correct answer. But in this class, we're only going to ever really, on a quiz or a test, be working with ones that have one correct answer. Okay, so m is g of x is f of x plus 1 plus 2. All right, so that's f of x plus 1 on the inside. That's going to be left by 1. And plus 2 on the outside. That'll be up by 2. That's the kind of double transform I'm going to be working on with you. Or one like this next one in f of x divided by 2. Okay, I'm going to horizontally stretch by a factor of 2. And then I'm going to subtract 3 on the outside, so I'm going to go down by 3. And that's what we mean when we say describe the graph of g in terms of the graph of f. Just I kind of write down some transforms that happen to the graph of f to get to g. Alright, so for this next one, I've got f of x equals x squared, and I've got 8 of these functions where I'm going to want to sketch a graph, write an equation, and compare it to the graph of f, like, describing the transforms. So I think what I'm going to do, I'm going to bring in a more professional drawing of y equals x squared. Yes, this will be perfect. So I'm going to start with a, f of 2x. So f of 2x is I'm going to take 2x, and I'm going to square it. And this is something that I didn't have happen yet that we need to be careful about. We need to square the 2 and the x, so this would be 4x squared. Okay, so what's going to happen is it's going to be twice as narrow. Because f of 2x, this is a vertical, or pardon me, a horizontal compression by a factor of 2. Oh man, this is not a very good sketch, but it doesn't have to be. I'm just trying to give you a sketch. Write an equation, sketch graph, compare the graph. Okay, so horizontal compression by a factor of 1/2. F of x plus 3. Okay, so b of x, okay, I'm going to take x plus 3 and square it. And of course I did not leave enough room on my graph for that, or yeah, I'm going to need a much larger scale graph of y equals x squared, but I'll do that after this one. I'll do the best I can here. Okay, so x plus 3 squared, okay, we saw one like this in the examples, in the notes. Okay, it shifted it left by 3, and I'm just going to do this, and I guess all we'll be able to see is the right half, but we know that the same thing would be happening over there. And so we're just going to say left by 3 and get ourselves a better original to draw on. All right, I think that'll be good, at least for a couple more of them. Okay, f of x plus 4 on the outside for c. So c of x is going to be, okay, f of x is equal to x squared, and then I'm adding 4. All right, so x squared plus 4, we're good at graphing something like that. This is going to be a standard parabola, but shifted up by 4. Okay, so up by 4. Okay, oh, I know what I can do. I can just take only the parabola itself and just get completely rid of the scale, which is how I would usually sketch, I think, and just go from there. All right, but d is going to be f of 1/2 x. So I'm taking 1/2 x, and that's what I'm squaring. Okay, so if I square that, I'll have to square the half and the x. And so I end up, okay, everything is twice as wide, so I'd be over here and over there. 1/4 of 16 is, yeah, that's 4. Okay, and then we would see that it's twice as wide. Okay, so I would say horizontal stretch by a factor of 2. It's looking like E is one I'm going to need to graph on my own, so E of x is negative f of x minus 1. So that's going to be the negative of f of x minus 1. F of x minus 1 is going to be taking x minus 1 and squaring it. Okay, so I might do that in the brackets first and then make it negative afterwards. Okay, so if I square x minus 1, I'll have an x squared, I'll have a minus x and another minus x, that's a total of negative 2x's, and then a plus 1. I'm taking the negative of all those things, so I've got negative x squared plus 2x minus 1. And I'm kind of realizing that might not have been the way to write that. I think maybe the original way it was written might have been best for us, because that's vertex form, and we're able to graph when it looks like that. I've got the negative of x minus 1 squared, so it's going to be a downward facing parabola with vertex at x equals 1, y equals 0. Yeah, that's, I'm going to get rid of all that. So the original thing was a perfectly fine equation, but if I needed to write it in standard form, that's what I would have done. So I'm going to sketch the graph of the original. Negative of x minus 1 squared. Okay, so I went right by 1, and then I'm reflected across the x-axis. And I think, yeah, you could have looked at it as reflect across the x-axis and then move right by 1, and this is a good picture of why you could do either of those in either order you like. All right, so we're going to say right by 1, and then reflect across the x-axis. Next one is, okay, 2 times f of x plus 3. So it's going to be 2 times x plus 3 squared. Wait, whoops. I mean, I guess it would be the same thing, but I really wanted to show it like that. And yeah, I kind of like writing it like this again, because this is pretty much vertex form, so that's 2 times x plus 3 squared, because the only thing I'm squaring is the x plus 3, not the 2. Okay, so this is going to be like y equals x plus 3 squared, which would just have its vertex at x equals negative 3 and y equals 0, but it would be twice as tall. And, earlier in the course, we kind of interpreted that as just being narrower, but it's kind of the same thing. So here's f of x, and I might draw this one a little bit wider this time so that when I go to do the narrower one, it's a little more obvious. So I've moved to the left by 3, and it's twice as tall. So I'm going to just make that negative 3, and I'm going to make sure to make it, real narrow, twice as tall. So you can see that it's been vertically stretched and shifted to the left. Okay, so this would be a vertical stretch by a factor of 2, and left by 3. It would not matter what order. Right, so, oh man. Okay, so what I'm going to do is I'm going to just plug in 2x minus 6 right here. So 2x minus 6 squared. Okay, and then I'll show you that we could write 2x minus 6. That's kind of a loaded question, right? Because that's 2 times x minus 3. And this is one where we would have to worry about the order in which we transformed these things. But I think maybe we can just do a little bit of factoring first. So that 2x minus 6, I can write that as a 2 times x minus 3. And that's still what's getting squared. So I might call that 2 times x minus 3. So I'd be squaring the 2 and squaring the x minus 3. So really what this would look like is, okay, squaring the 2, that's going to give me a 4, and squaring the x minus 3, it'll look like that. Okay, so we could interpret this as right by 3 and vertical stretch by a factor of 4. But if you looked at f of 2x minus 6, this looks like 2 horizontal transforms. So, I think I'm going to, if you want to talk about it as 2 horizontal transforms, be my guest. Give it a shot. But I'm going to just work on this kind of looking at it, it's multiplied by 4 on the outside. After doing some simplification, it's all the same thing. If you're interested, come talk to me about it. If not, I think this is the easier way to go. Okay, so this will look very similar to the other one, except I'm going to go right by 3 and then vertically stretch by a factor of 4. So this one's going to be extremely narrow. Yeah, I'd say that looks narrower. It's taller. Okay, however you want to think about it. Either way, we're going to go right by 3 and vertical stretch by a factor of 4. Alright, now the last one is h of x is negative 1/3 f of x plus 2. And this is going to have 3 different things going on. But I do like it because, we're working on a quadratic, so it would be somewhat familiar if you remembered anything about vertex form. So I'm going to say h of x is, what we're doing is we're taking negative 1/3 and we're multiplying it by f of x, which is, that's just x squared. Okay, and then we're adding 2 on the outside. So negative 1/3 of x squared plus 2. Alright, so really what's happening, I might do this kind of in stages, is, okay, we've got our original y equals x squared. Ooh, that was a little rough, but it'll do. And then negative 1/3 of x squared, well, that's just going to serve to, make it wider and upside down. We already knew that. And then if I add 2 to it, it'll just move that up by 2. And so maybe I can even do that. Thinking about, okay, my negative 1/3 x squared plus 2, that'll just be up there, and that'll be what I've got. So what happened here was, say I reflected across the x-axis first. Then I got horizontally compressed by a factor of 1/3. Vertically compressed. Factor of 1/3, and which is actually the same as a horizontal stretch, right? You can look at it that way. And then we moved up by 2. And that's all for these transforms of x squared. Okay, now I think this one is going to seem like a bit of a reprieve compared to the last one. Yeah, f of x equals natural log x. This is really, I just want to remind you about all of our function types and what their graphs look like. Okay, natural log x is the one that's got a vertical asymptote at x equals 0. because there's no exponent I can put on e to get 0, and then otherwise it kind of looks like a sideways exponential. Okay, g of x equals natural log of x plus 1. Okay, well, that would just serve to shift left by 1. So I'm going to just say, all right, well, wherever I decide x equals -1 is going to be, which I think will just be like the left edge of what I can see on the x-axis. I'm going to be approaching that, and then, okay, this was an intercept of 1, 0, because the natural log of 1 is 0. And then otherwise it should be pretty much parallel. Okay, and then that's going to be g of x. So versus f of x was natural log x. All right, the next one is 2 to the x and then 2 to the x plus 1. So 2 to the x is a exponential growth curve. So that's y equals 2 to the x. 2 to the x plus 1 will just be shifted up by 1. Okay, so I'm going to just try to make that happen, make this as parallel as possible. So it's the same graph, just shifted up by 1. Everything being 1 higher than it was otherwise, I don't know, it's kind of hard to draw. But that would be y equals 2 to the x plus 1. Next one's got y equals square root x, which is just kind of a sideways parabola. And y equals square root of x minus 2, which is just going to be the same as the graph of y equals square root x, but shifted right by 2. We did that a little bit when we studied radical functions. We just kind of looked at it instead of thinking about shifting the graph right. We just thought about where does the domain start, and it started at 2 instead of 0. But if you think about it, it's actually the same. So I go over here to where 2 is, and I draw the exact same curve. Ooh, man, let me see if I can try that again. Yeah, I think the curves actually grow closer to each other, so they don't look as parallel as you might want them to be. But that's y is the square root of x minus 2. Oh, ooh. Much better. And the last one is f of x equals x cubed, which is going to look in general like the graph of y equals x squared, except it goes down on the left side. And -2x cubed, okay, that'll be twice as tall or narrower, but also upside down. So I'm going to say there's kind of two things going on here. Might describe them as a reflection across the x-axis and a vertical stretch by a factor of 2. But either way, it's just going to be, just a little bit more dramatic. That's maybe a little too much, but you get what I'm saying. It's going to be taller and skinnier, and it's going to be upside down. All right, now this next one I threw in, I think, because I wanted to, what am I getting at here? Okay, definitely the quadratic thing, where we have to be careful about the parentheses. I see that happening. I think there was some other message I was trying to convey to you in this problem, but I'm not exactly seeing it. So write an equation for h of 5x. We can do that. H of 5x, wherever I see x in the original equation for h, I'm going to replace it with a 5x. So that's going to be two places. H of 5x will be equal to 5x squared plus 3 times 5x plus 4. And if I square 5x, I'd be multiplying 5x times 5x. I'd have 2 5s and 2 x's, so it'd be 25x to the 2. 3 times 5 times x, that's going to be 15 times x, and 4. Okay, so that's h of 5x. And describe the graph of h of 5x. It's like the graph of h, but horizontally compressed by a factor of 5. Or maybe 1/5. Horizontally compressing the graph of h by a factor of 1/5. Right. That's all they're asking about h of 5x, so I'll get rid of that. C is write an equation for 6h of x plus 1. So 6h of x plus 1. First I'm going to find h of x plus 1, and then I'm going to multiply it by 6. So what I'm going to do is each time I see x in the equation for h, I'm going to replace it with an x plus 1. Okay, and it just said write an equation, so I think that checks the box, right? We wrote an expression for it, that is an equation, right? If we needed to simplify that, it would be kind of a lot, but it's something we could do. Maybe I'll do it for you. X plus 1 squared, I'm going to have to do FOIL, but I'll have x squared plus 2x and 1. I'd have to distribute the 3 over the x plus 1, so I'd have 3x plus 3, and then I'd be adding an additional 4. So this would all end up being 6 times x squared. In terms of x's, I've got 2 plus 3 of those. And my numbers, I've got 1 plus 3 is 4, and 4 more is 8. It is not factorable. Okay, but then I could say that's 6x squared, 30x, and 48. And I don't know how much better off we were than we were before. We're not going to be sketching this quadratic or anything, but if you needed to simplify it, that's how it would go. Okay, if I was to describe the graph of 6 times h of x plus 1, I would say it got moved to the left by 1, and 6 multiplied on the outside will be a vertical stretch by a factor of 6. And then E, now this is something I haven't asked you. I haven't gone forward and been like, hey, stretch this thing by horizontally by a factor of 2, write an equation. And so I guess that's something I need to make sure I'm direction I'm approaching you from. But here we are, we're doing it once here, and give you some practice problems along the way. Keep building the skill. So J is formed by horizontally stretching the graph of H by a factor of 2. So I think what you need to remember from before is that a horizontal stretch by 2 is where we are replacing x with 1/2 of x, because these horizontal transforms, they work the opposite of the way we expect. Okay, and so I'm going to say, all right, j of x is going to equal h of half x. And write an equation for j of x. Okay, I guess that would be an equation, but I think I want like an explicit equation. And what h does is it takes a thing, squares it, and adds 3 times it, and then adds 4. So it's going to be half of x squared plus 3 times half of x plus 4. And if I was to square it, to write this in standard form, which maybe you need to because you have to match up something against multiple choice where all the answers are in standard form, that would be a situation where we would have to do that. Okay, and what do you want to bet? One of the answer choices would start with 1/2 x squared. Okay, so 1/4 x squared, because I'm squaring the half and the x, plus 3 times half of x is 3/2 x plus 4. Okay, and that would be a good explicit equation for j of x. Alright, now the last one, now this is, I think I just threw this one in because it had been, this is one of our graph types, but we hadn't talked about it on this homework or this notes, 1 over x, right? We just learned about it. So first we're going to write an equation for f of x minus 2. So I'm going to say f of x minus 2 is going to be wherever I saw x in the original equation for f, I'm going to replace it with an x minus 2. So that's 1 over x minus 2. Describe the graph of f of x minus 2. Well, it's going to be like the graph of y equals 1 over x, but shifted to the right by 2. Okay. For C, it's asking about f of x, then subtract 2. Well, I'm just going to say f of x minus 2. Well, f of x is 1 over x, so it's going to be 1 over x minus 2 on the outside. And how I'm describing that in terms of the graph of 1 over x, I'm going to say, well, that's just down by 2. So we're going to shift down by 2. Alright, and then for E, if the graph of G is formed by shifting the graph of f up by 3, so I shifted up by 3, and left by 4. Well, left by 4 is where I replace x with x plus 4. Write an equation for g of x. There we go. Oh, wait, but I could be a little more explicit, right? Because we know what f does to a thing. It does 1 over that. So this is going to be 1 over x plus 4 plus 3. So I went left 4, up 3. And this is exactly the type of thing we spent a lot of time graphing in the last unit. You already know how to do that. You don't need to watch me do it. You don't need to do it yourself. Just zoom out for a second and make sure, yep, that's all the problems we got here. That's going to be all for this homework. Thanks for watching. Really hope this helped.